Hi, Assalamualaikum and a very good morning. So now we are in chapter 4, which is Introduction to Organic Chemistry. We're going to focus on the subtopic of 4.4, which is Reaction of Organic Compound, part 1 of the video. So in this video, we're going to look into the explanation of covalent bond cleavage, which is homolytic cleavage and heterolytic cleavage. We're also going to look into the relative stability of the primary, secondary, and tertiary of the free radical, carbocations, and carboanion. So free radical will be usually denoted as A dot, which is a species with a dot. Meanwhile, for carbocation, it's usually a carbon and with a positive charge. Meanwhile, for a carboanion, it's usually a carbon in the middle with a negative charge. After we learn about the classes of the intermediates, we're going to look into the inductive effect of the alkyl group towards the stability of the free radical carbocations and carboanions, where all of these three is known as reaction intermediates. Alright, so without any further ado, let us start. So, all chemical reaction basically involve the breaking of bond and the formation of the new bond. So, the breaking of the chemical bond is known as fission. So, there are two types of covalent bond fission or the bond cleavage, which is the homolytic cleavage as well as the heterolytic cleavage. For homolytic cleavage, the atoms here, the electron here will be divided equally, where one of the electron going to be passes to atom R and one of the electron here going to be passes into atom X. Okay, and this can also be represented using a single bond, because a single bond here refers to two electrons. So one electron, which is denoted by half-headed arrow, will be transferred to one atom, and another electron will going to be passes to atom X, which is denoted by half-headed arrow. This one is a full-headed arrow. This one is half-headed arrow. Here refers to the transfer of two electrons. Here, half-headed arrow refers to a transfer of one electron. So we're going to use this for the homolytic cleavage. Meanwhile, for the heterolytic cleavage, the electron going to be divided unequally, tidak sama rata. Maksudnya, dua elektron tadi akan dipindahkan kepada salah satu daripada spesies tersebut. So the two electron going to be transferred to one of the species here, and usually the one that will be taking the two electron, going to be the most electronegative atom. So for this case, the two electron, for example Rx here, the two of them going to be transferred into R. So we use full-headed arrow, which refers a 2 mole of electron. So to learn more about this, let's look into the next slide. So homolytic cleavage, as I mentioned before, it is a bond fission in which two electrons of the covalent bond are split equally between the two atoms joined by the bond. So two electrons here, for homolytic, each atom gonna get one electron, and this process is known as homolysis, where each atom gets one electron and the resulting species are known as the free radical. Okay, so this is the process here, where one electron get to B and one electron get to A and produces free radical A and free radical B. And the free radical here is known as the reaction intermediates. It is very, very unstable and therefore very reactive. Means that it's going to take part in the chemical reaction. Okay. Now for the heterolytic cleavage, it means that the type of the bond fission in which both electrons of the covalent bond remain on one of the atoms. So, for example, we have Rx here. So the two electrons going to be transferred into R because R is more electronegative atom. So, and the heterolytic cleavage will produce positive and negative ions. So the negative ion will be the more electronegative atom, and it is the one that pull electron density towards itself and therefore will carry a negative charge. Alright. Meanwhile, the species that not gotten any electron will carry a positive charge. Okay. So the two shared electron will be split unequally between the two atoms. So in this case, A and B. So B is more electronegative. So A is gonna be A plus cation because it does not get any electron. Meanwhile, B here gonna carry a negative charge and it receive 2 electron. So it's gonna be an anion. Okay. However, if A, let's say atom A is more electronegative, we can say that A going to A, meanwhile B will not getting any electron and therefore positive charge. So it depending on the electronegativity of the atom. Alright. So now, as mentioned, reaction intermediate are basically a product of one step. For example, just now, Rx, right? So it's going to be transferred into R. So the product here, which is the negative charge, gonna now be a reactant for another reaction. So a reaction intermediate is basically a species that is the product of one step, which is this one, and the reactant for the next step. So it become the product. Now it's gonna be the reactant for the next step. And this is the situation here is called the reaction intermediate. Right? So there are three types of reaction intermediate. First, we have the carbocation. Second, we have carboanion. And third, we have free radical. As mentioned, carbocation will carry a positive charge. Carboanion going to carry a negative charge. And free radical going to be represented by a dot. Okay? So all of these reaction intermediates are very unstable and highly reactive. So now let's look into the carbocation first. So it's a very reactive species with positive charge on carbon atom, and this is formed due to the heterolytic cleavage. Okay, so as mentioned here, this is the heterolytic cleavage, and you know that the carbon gonna carry a partially positive charge, meanwhile chlorine gonna carry a partially negative charge. So the electron density. Okay, so we know that chlorine is more electronegative than carbon, and we know that this bond are polar. So the two electron here going to be attracted to the more electronegative atom, and hence the chlorine going to carry a negative charge. Meanwhile, the carbon here, which doesn't get any electron, will carry a positive charge, and the positive charge here is known as carbocation. Okay. All right. And the CCl bond breaking heterolytically, and both the bonding electrons are transferred into chlorine to form anion and carbocation. Meanwhile, for carbon anion, it is a very reactive species with a negative charge on the carbon atom, so negative charge. And also similarly, it will form by a heterolytic cleavage. So let's say if we have CH3C connected with a lithium metal. Okay, just now in chlorine, but for carboanion, it is connected with a metal. So it can be sodium, magnesium, or potassium. All right. So you know that the metal is usually a electropositive atom. So the carbon here going to carry a partially negative charge. So the electron density going to be pulled through the carbon. All right. So 2 electrons here going to be transferred into chlorine, and that is why we are using full-headed arrow, because 2 electrons are transferred into there. And hence, you can also put 2 electrons here or denoted it as a negative charge because these are species that receive the electron. Meanwhile, the lithium plus here going to be the cation. Okay, so as mentioned, the Cl bond breaks heterolytically, and both the bonding electrons are transferred to carbon atom to form carboanion and cation of lithium. Now, for free radical, is a very reactive species with an unpaired electron. So it is formed via homolytic cleavage. For carbocation and carboanion, it is formed via heterolytic cleavage. But for free radical, it is formed via homolytic cleavage because it is shared equally between the two atoms. Alright, so it is very reactive because it seeks for another electron, one more electron in order to complete its step. For example, the chlorine here. So the chlorine has the same electronegativity because both chlorine atom. So the chlorine bond here going to be transferred equally, which a half-headed arrow here, which refer to the transfer of one electron and the transfer of one electron. So the Cl atom here going to be getting one electron each, and it's going to be a chlorine free radical. Also, you can use it for carbon-carbon single bond here, because carbon and carbon here will have the same electronegativity. So it will undergo homolytic cleavage, one going to here and one going in here, and the condition are very strict. So you need not miss out the UV, because UV here is very, very critical. You need to include that for homolytic cleavage. All right. So the chlorine going to be separated there. The carbon-carbon bond here, sorry, will be break, and one electron will be transferred on this side, and another electron will be transferred to the other side. Okay, and this will produce free radical of the carbon chain. Now we're going to look into the class of the carbocation. So the carbocation, carbanion, and free radical can be classified into primary, secondary, and tertiary. So let's look into the carbocation first. Okay, carbocation first. So in order to know the class, it will be dependent on the number of alkyl group that are bonded to them. So alkyl group here, basically CH3, C2H5, and another stuff. So basically it refers to a carbon chain. Okay. So let's look into here. So let's say we have carbocation, but it is attached with hydrogen. This is known as methyl-cation. However, when the carbocation attached with the alkyl group, which can be CH3 or C2H5 or another long chain, it's going to be a primary carbocation. All right. So if the carbocation is attached with two alkyl group, it's going to be secondary carbocation. Next, if the carbocation is attached with three, then it's going to be tertiary carbocation. Alright. Now, the same thing apply to the others. For example, carboanion with no alkyl group is going to be methyl carboanion. If there is one alkyl group, which is the R or the carbon chain, it's going to be primary carboanion because negative here. If got two, secondary carboanion, and if got three, tertiary carboanion. For radical, the concept is still applied. So it's still depending on the number of alkyl group that are bonded to the carbon. Okay, so if there is none, it's going to be methyl radical because dot here. If got one, it's going to be primary radical. And if got two alkyl chain bonded to the radical, it's going to be secondary free radical. And if got three alkyl group, it's going to be tertiary radical. All right. Now we're going to look into the inductive effect of the alkyl group. So the one that is bonded just now, which is methyl radical, methyl primary, secondary, and tertiary, on the stability of the intermediate just now. Okay, so we're going to see the effect of the alkyl group. So basically, inductive effect are basically an electron donating effect, and it is the pool of electron density through the sigma bond caused by the electronegativity or the charge difference of atom. Okay, so the alkyl group, the one that R group just now, will have the electron donating effect. And because of it having an electron donating effect, it will increases the stability of the carbocation and the free radical. Okay. However, okay, so the higher the number of the alkyl group, for example, the primary, secondary, and tertiary, so the tertiary will have more alkyl radical, right? The alkyl group, right? So it will increases the stability of the both carbocation and the free radical. However, The alkyl group will decreases the stability of the carboanion. So let us look into the example here. So the inductive effect on the alkyl group, which is R primary, if got 2 going to be secondary, and if got 3 going to be tertiary, on the stability of the free radical. Alright, so radical, so we're going to look into the radical first. So when there is an increase of the alkyl group, the stability of primary will be higher than methyl. If they got 2, these two, the secondary radical going to be more stable than primary and methyl radical. However, when there is a 3 alkyl group, it's going to be more stable than both secondary, primary, and methyl radical. Alright, why is that so? As mentioned, the carbon free radical here is very reactive and it needs electron. Okay, it needs electron in order to be octet. The R here, as mentioned in the previous slide, it has an electron donating ability. Okay, so when there is more of the alkyl group attached to the radical, it will be able to donate electron density more towards the radical, hence it appears to be more stabilized. However, when there is no electron donating ability, the radical here is not stabilized and therefore it's going to be the least stable. Okay, so least stable, this one more stable. Okay, so we can say that the stability increases from methyl radical to tertiary radical. Now we're going to look into the metal carbocation. So for metal carbocation, it's basically the same as the free radical. So the primary carbocation going to be more stable than the metal carbocation, and the secondary carbocation going to be more stable than these two. Meanwhile, for the tertiary, going to be more stable than these three here. Why is it so? The same concept is applied to the free radical and the same reason for the carbocation and free radical. This is because the carbocation here, because it has a positive charge, it means that it has less electron. So it needs more electron in order to stabilize it. The alkyl group here act as an electron donating group, EDG, electron donating group. So it will donate electron to the C plus here, to the carbocation. So when there is more inductive effect by the electron donating group, the carbocation here going to be stabilized in comparison to the methyl carbocation and the others. Okay, because it got 3, so it will be more stabilized. Hence, this is going to be the most stable. Here going to be the least stable. Okay, so the stability increases from methyl carbocation to the tertiary carbocation. Now, we're going to look into carboanion, which is a negative charge on the carbon atom. Okay, so now it is going to be the reverse way. So the methyl carboanion is much more stable than primary, and it is much more stable than secondary and tertiary. Okay, this is because the tertiary carbocation here is already have lots of electron. Okay, it has lots of electron, and that is why it carries a negative charge, and it does not need any more electron. It needs to release it in order to be stable. However, because of the presence of the electron donating group, which is the alkyl chain here, it will keep on donating to the C minus here. So it will become more unstable and become more unstable because the C minus here has already got many electron, and the alkyl group keep donating the electron to the C minus, and it will become more unstable and unstable and unstable. in comparison to the methyl carboanion here. Alright, so for this thing, we can say that the stability decreases from the methyl carboanion into the tertiary carboanion. Alright, so I think that's all for today's video. See you again some other time. Bye!